We can watch 14 nanometer. Let's take a look here.
11 years of work on the Tri-Gate transistor combined with an amazing...
Tri-Gate transistor, we saw the scanning electron microscope. I put it there. That was a 20
battery active life, almost 2x the battery life on things like a Mac Air. The first family systems we showed Brian yesterday, and up to twice the graphics performance. And really, that's just the beginning. Broadwell, you saw yesterday, already operating in an Ultrabook form factor. We're seeing amazing 2-in-1 designs coming on Broadwell, a broad range of new family systems based on Core with performance significantly above what an Atom or ARM architecture can deliver. Significantly greater performance and much, much lighter. So what I wanted to show you is, we showed you in the form factor yesterday. Now I wanted to show you something directly out of the labs. So first, let's just say what does 14 nanometer do for me from a form factor perspective. This is the Haswell Y product that was 6 watts and 4.5 watts. And this is the Broadwell Y product. So you can just get a flavor for just how thin and small the 14 nanometer products become as we go to the next generation chip technology. Here in front of me is something directly out of the lab. And so what I wanted to do is to show you Broadwell is going to enable 2 different kinds of devices. One, you can plug the chips directly into the existing systems. And second, we'll have brand new systems with a broad new range of fanless designs. So what I've done here is I'm normalizing a Haswell Y-based system and a Broadwell Y-based system. And I'm going to run Cinebench, which is a CPU-intensive benchmark, just so I can show you the benefit of what 14 nanometers power reduction at the same performance levels just by moving socket compatible from the Haswell to the Broadwell.
It's not a YouTube.
Without even a lot of performance tuning that we'll do in the next month. So we're really, really excited about where 14 nanometer is.
Does this look like any graph we just saw?
We're really, really excited about where 14 nanometer is. 2 different kinds of devices. One, you can plug the chips directly into the existing system, seeing a %.
What graph is that? Power versus time for workload. Some workload he ran. Here is the power versus time, and what are these curves? What are the 2 curves? There's 2 different colors, so what does it mean? Yeah, which is the 14 nanometer? Yeah, orange. So what it is showing here is the same instruction set architecture, which was the Intel, right, ISA, implemented in device technology of 14 nanometer, and I think this other one was 22 nanometer. Here we're seeing the effect of shrinking the transistor on power, but not changing the instruction set. Same instruction set, same workload, versus time, and you can see that this is a pretty boring workload, but right, the power dissipation varies over time. I'm having some feeling that this might be cumulative, this might actually more be energy, but anyway, this is power versus time for this workload. Maybe this is part of the workload where it's just static and just in a loop and not doing anything new. Yes, sir?
I was going to say, even the idle has a lower power.
Yeah, you're right. So this is very cool. So this is the difference between, so this is another question that comes up in my notes because we're just starting out and it's enough, you guys have enough, is we have static power consumption and dynamic power consumption. In this class, we only, in our equation, I just gave you the C V squared F. We just do dynamic power consumption. At C V squared F is P. Okay. This is for switching. When the transistors are switching on and off, we're crunching bits. Okay, we're switching. The transistors are turning on and off. But there's also static power. Static power is what we call leakage power. This is in standby mode. We're not doing any computation. The transistors aren't even switching, but just the fact that we have a substrate with metal lines and power and ground connected together. There's a resistive path from power to ground, and it turns out that this usually is smaller. Static power is less than dynamic power. But as we reduce V, These two are getting closer together these days. This is a graduate course, okay, but it's a graduate topic. But if you look, the equation in the study sets, it's just the dynamic power. There's actually V equals IR. So this is just a resistive loss, resistive. It's not related to F, because F is, there's no switching, okay. So some people ask sometimes, where is the missing term for the static power? If you're into these things and you're a more advanced student, we just do, in this class, we just do the dynamic power. They both add in. This is becoming more and more important these days. You'll get it in computer architecture course. Right now we just do dynamic power, which is still the majority. So does that make it real? Broadwell is just 1 year old, 1.5, right? All right, so here's a problem that's in the study set. Let's solve this one, put everything together, and it's our last material for this module of device technology. Put everything on one problem that fits in one slide. Sounds kind of like the lab, right? So given instructions on a prototype system has the following characteristics. This is the program we want to execute. This is a data sheet that says a set is a CPI of 1, energy of 1 nanojoule. Add 2 CPI, 2, okay, so forth. These are different instruction class. What's taught? Totally realistic. Someone can hire you to do this. If the processor clock cycle is 333 picoseconds, calculate the energy to complete the execution of the program above. That means the entire program from start to finish. Also calculate the throughput metric of MIPS per milliwatt. So without lifting a pencil, without even writing anything, what's the clock rate? How many gigahertz? 3. 1 over, right? So 1 over 333 pico is how many? 333 pico. I think of it this way: 1 nano is 1 giga, right? 1 nano to the minus 9 is 1 over, right? 9 is giga. So how many nano is 333 pico? Anybody raise your 1? Yeah.
It's 1/3.
It is 1/3, exactly. Right off the bat, I know this is 3 gigahertz. We're going to make it real, right? Human terms. And then what else is going on here? What's happening in this program? Is it straight line code? Is there any looping going on? Yeah, we see some branching. So this is going to happen a lot of times. So I need to figure out what happens when this executes as a loop. Are there multiple classes of instructions? Yes. Each one takes a different amount of time, and each one has a different amount of energy. What I'm going to notice is when this thing runs, I have energy for each instruction, so it doesn't matter the time. It's easier actually to calculate the energy first, and once I have the energy, I can get MIPS per milliwatt by using the time. The time is going to be based on the CPI. Why did I know the time is based on CPI? What does CPI stand for? Clocks per instruction. I said clocks are what? The native unit of time. Clocks are native unit of time for a CPU. If I talk about the clock cycles, right, the number of clocks, that's like I said, electron volts, right, is the native unit if you're working with a few atoms worth of energy. Okay, so this is time. This is telling me time. This is telling me energy. They want me to calculate energy. I'm just going to go for the energy first. Let's do that. That's what I'm saying here. Energy is independent of the execution rate. Does that make sense? Energy is. What about power? Is power independent of execution rate? No. All right. Power is the instantaneous energy. So that's execution rate coming in. Let's do the energy first. So energy consumed can be independently added, which is what I just said, of each instruction. So this program, let's figure out what instructions are executed. There's one set, because it's only done once, and then 2 read, 1 write. Set and the 2 reads happen before we enter the loop. Here's the loop. Go to step 4. And then 1 write at the end. We good? How many times do we go through the loop? 5,000? How many instructions are in the loop? Well, 1 add, and 1 branch. So how much energy is that? Add it up. You have 1 set at 1 nanojoule. You have, I'm going to work with the units in nanojoules. See, 2 read at 8 each, and 1 write at 8. This is a load store class. Are we good for this part? And what about the loop? 5,000 times through, you have 2, 2, and 3. Add, and branch. 2, 2, and 3. You figure it out, it's 35,000, 25 nanojoules. How many microjoules? About 35. All right. So you're halfway there. You got half the credit. What's the next part? MIPS per milliwatt. What kind of metric is that? Right? We had time metric. We had throughput metric. We had energy metric. MIPS per milliwatt. If you had to use some words to describe it, what kind of a metric is it? It's power and throughput combined. It's a composite metric. It's a composite. Power is watts. You're right. Power's in there, but also throughput. MIPS is. We have multiple types of MIPS. Right? A MIPS processor. We have a. What does this stand for in this context? Million instruction per second. So that's throughput. Anytime we have something per unit time, throughput. Okay. And we had a question. Yes, Mr. Smithson.
I was going to say what it was. Sorry.
Okay, you got it. It is a composite metric, and MIPS is a million instruction per second. Since we have energy, we can get power, right? How do we get energy and power? What's the opposite of this? Divided, derivative. Okay, so we're going to take this, right, and divide it into the time, but we have to find the execution. How do we find the running time of this program? Good question. I look for a raise of hand. Mr. Smithson.
You add up all the time it takes to complete every instruction?
Yep. And how do you get the time for every instruction?
You calculate the amount of clocks it takes and you divide that by the amount of time that every clock takes.
And you're totally right. So we know here we're running at 333 picoseconds per clock, and this one takes 1 clock, this one takes 2 clocks. So for example, how many nanoseconds does add take? You got it, 0.666, 2/3. Why? Because each clock is 333, so it's going to be 2 clocks to 666 pico, which is 0.67 nano. This is time. Okay, I know it's a CPI. Don't get a mental block. It's time. All right, how do you convert it? Human units of time, we multiply times the clock cycle time. It's in the equation. That was in Module 3. You can go through that process. What I did is I just used the units. The native units is clock, which I think it's easier. You can do all your nanos and just figure out how many clocks. Then we know that that's that many clocks. This is the number of picoseconds per clock. Watch your units. You end up with so many picoseconds, a whole bunch of them, which is that many nano. Then what? How many MIPS? How do we get MIPS? Yeah, go ahead. Yeah, you're good. Go.
We take the amount of instruction and divide by second.
You got it. And how we know how many instructions in here because we just calculated them up here, but we added, this is the joules, so just get rid of the joules. Okay. So we did that here. Do convert to million. That was the 10 to the 6 in the equation in Module 3, right? There was a 10 to the 6 we divide, right? Anyway, that's that many millions of instructions per second. And then we're going to just take MIPS per milliwatt. So this is how many joules divided by the time is watts, converted to milliwatts, factor of 1,000, and then divide that right into your MIPS per milliwatt. If you go and if you look back, I think I gave them some previous slides, MIPS per milliwatt. So I think, all right. Now we see this. We see how this is calculated, right? I think I had multiply, accumulate. Let's see. We had it's over here somewhere. Let's see. Yeah, here we go. MIPS per milliwatt. So what we're seeing here is the energy over time, which is power. This is the instantaneous energy dissipation. How much energy dissipation per time that got applied to generate so many number of MIPS. So this is a composite metric. It's throughput and power working together. Okay. There's all different types of metrics. Sometimes you care about one metric, sometimes you care about another. Sometimes you just care about total energy. Total energy is going to relate to battery life, as we see here. These are very low energy processors. Okay.
Why do we use MIPS instead of just like instruction count or instructions per second? Why do we have to put it in MIPS? Is it just because it's a bigger number and it's easier?
Yeah, it's just making it so we don't have so many zeros. That's all. It's just like you get your electric bill. What is it in? Is it in watts? It's in watt hours. What is it? Kilowatt hours, right? Because otherwise it's not even, you don't even get it, right? So there you go. Yeah, it's just human convenience. Gigahertz, right? It's just instead of hertz, right? We just say gigahertz. So we say MIPS, millions, but it's probably GIPS, okay? Because when MIPS was invented, we were at megahertz, but now we're gigahertz. But okay. So we're at the end. I'll let you ask questions first. Any questions on it? I think it brings it all together in a nice, concise example, and seeing all these terms working together, relating to the video we see, which is Intel today, right? Last year, and what? Some other data that we have, some equations that we have. It's not like it's floating in the air. It's a real thing. I'll let you ask questions. Relates to your project. You get to do your code. Yeah.
When you find the overall CPI of those,
you can find overall CPI as a weighted average. To me, it's making it more complicated. I would just count the number of clocks using this clocks per instruction, and then multiply times the clock rate, cycle time, 333. You can also, is it John? Jack. Well, John, I see. What he's suggesting is correct. You can go, remember we had weighted average? But then you have to know like what percentage, because this is like 15,000 instructions, what percentage of those was add? What percentage of those was? You can calculate it, then calculate the effective CPI, and then multiply that times the 15,000, you'll get exactly the same number, but it may be a lot more work. But it's totally correct, yes. So that's a good insight, connecting together what we already learned to this, in this example, the program. And it's not too huge. But suppose this is like some Amazon Turk. What's Amazon Turk?
This old system where you could like pay somebody to like...
It's exactly right. Speak up. Go ahead. Yeah. These micro jobs, right? They come. Go talk, and then I'll find out. Cause while you're talking, it'll give me a chance to find this coolness. Okay, go ahead.
Well, like you would it was like.
So Jeff Bezos, he wanted to keep impacting the world and do great things, right? Since he has one click and a patent on one click. What's the patent on one click?
One click checkout at Amazon Shopping.
Yeah, and even like iTunes, you buy a song or whatever, they have to pay him like 1 penny. It's true, because he patented the idea of clicking to buy. What? Everybody wonders the same thing, but the patent office says it's valid and it's been challenged, and there you go. So while he's done with that, he wanted to go to his next thing. He said we can have people contribute. You make these small little jobs, and you get paid, $1. And then it's so this.
It's named after the.
There you go.
Chess playing machine.
Exactly. That's why I was going to show you the coolness. Yeah. Okay. So tell me about that. Yeah. Go ahead.
There's some chess grandmaster just hid inside of looked like a mechanical man, and like it could
exactly right.
War, and he defeated defeated Napoleon, for instance.
It was actually the best scientists in the world couldn't figure it out for about 50, 100 years. This mechanical Turk, maybe we get an image here. So there was a magician, saw people in half thing. And so this guy had what they thought was like AI, okay? He built this mechanical machine that could beat the world's best chess player at the time. It turned out he was hiding inside the box, okay? But anyway, Mechanical Turk was this like mystery machine that could do intelligent things kind of automatically. So that's the Amazon Turk is our modern day equivalent. So if this stuff's interesting to you, you can Google it. It's kind of interesting. Okay, so yeah, Amazon, maybe they want to they give you this code, and it's not just 7 instructions, right? Amazon, the Mechanical Turk, whatever is running to dole out these, you can sign up if you want to make some money, right? You can do it. Actually, they have you do these junk things, right? Like sealing envelopes. See, you guys are too young, but in the old days, like it says, work from home, packaging envelopes and stuff. But it's always a scam, right? But this way, I think, is like a medium scam. It's not that bad. They actually do pay you, but you probably do some junky jobs, like click on people's web pages and test them and stuff. What's the point? We probably don't have the full code for that, because Amazon doesn't want to give their code away for Mechanical Turk, because they have 200 programmers working for 10 years on it. So what do they give you? They give you the CPI. So then you're back to what Jack said. We can't calculate the number of clocks because they're not going to give us the code, but they're going to give us the average CPI. You're happy, right? Because then you can use the table with the weighted average. They already calculated it for you. Any other things we can do is recap, right? This is the last material for exam 2, which is next week. So we covered device technology in this module. I think enough to get you pretty much through any interview at a bachelor's level and get you motivated to grad school if this stuff's interesting. Maybe take some electives if this stuff is interesting to you. We start with photolithography. You should have some idea when it says 22 nanometers, what does that mean? You should have in your mind the ITRS roadmap. What was ITRS stand for?
Internet of Things.
IoT. There's ITRS, but just kind of, what range are you in and what number do you expect, and is it really new? That's really tells us if it's new. Okay, if you go to buy a chip and it says it's 45 nanometer and they say it's brand new, you're not so impressed and you're a little bit suspicious that, maybe it's not the best in the world. You should know the fabrication process. You should have some idea how semiconductors work. What does the word mean? Semiconductor, right? It's actually an insulator that can be made to conduct. Cost versus performance, okay? And we've seen a lot of examples of this. You should know the trends, Moore's Law, what it applies to. And then memory and CPU speeds is kind of going to motivate actually cache memory, which is module 11. It's coming up. And energy and power, okay?